Oaxaca. I know it's a long way for many of you. And okay, so we have Izzet Coskun from the University of Illinois, who will deliver 3 lectures on the stuff he's been researching these days. It's pretty interesting. Today, tomorrow, at 10 a.m. in the morning, and on Wednesday, 10 a.m. in the morning, here also. We have problem sessions, not today, but tomorrow at 4. So to informally discuss what's being said in the lectures this morning. And on Wednesday also. Problem session at 4, here also, in the institute, and here in this very room, to discuss what's being said also, 3 lectures. And so we have 3 lectures this week, and then we have the SIGA, Thursday and Friday, Monday and Tuesday, and then towards the end of the week, Wednesday, Thursday, and Friday, we have Maxime Fedorchik from Boston College, who will also deliver 3 lectures. Each lecture is 90 minutes roughly, and well, let's enjoy it. Thanks, Izzet, for coming over, by the way.
Well, thank you. I mean, it's great to be back in Mexico. Thanks for organizing this. So I want to talk about the following things. So X will be a smooth projective surface over the complex numbers. And then what we want to talk about is the geometry of the moduli space of stable bundles on X. Okay? So now let me explain a little bit what this even means. So what you do is you fix an ample. So everything will depend on an ample on X. So H will be an ample on X. And V will be a fixed Chern character. And we want to talk about stable bundles on X with respect to this ample H that has the Chern character V. Okay? So now let me explain a little bit what that means. So, first of all, sheaf for me always means coherent sheaf of pure dimension. I mean, you know, we don't worry about crazy things here. So, like, sheaf will always mean sheaf equals coherent of pure dimension. Okay? And what you want to do is you want to parameterize such sheaves on your surface, right? But the problem you run into is already if you look at P1, right? Already if you just forget that you are in a smooth projective surface, and I didn't write surface, so let me write surface. Suppose that you are even on something like P1 and say that you want to understand vector bundles of rank 2 and degree 0, there are infinitely many of them, right? So like you have like something like O of A plus O of minus A, right? And then for every non-negative integer A, you have such a bundle, and these are not isomorphic. So if you want to have a sensible moduli space, that's bad, right? Because, you know, we don't have, you know, infinitely many points is not such a good algebraic space. We don't know how to deal with those things. So the solution to this, you know, developed by Mumford and then Giesecker, Maruyama, and many other people in the 60s and 70s was to impose some sort of stability condition. So let's talk a little bit about what it means to be stability, so stable. So maybe the simplest thing to talk about is slope semi-stability. So let's make a definition. So a torsion-free sheaf is slopes, so you write it like this, mu h semi-stable, if the following thing happens. So first I need to define what this mu h is. Mu h is a slope function, so you define mu h of f as simply being the C1 of the sheaf dot h divided by the rank. And this makes sense because I assume that this is torsion free, so that, you know, my rank is not 0. So you say that a torsion free sheaf F is mu h semi-stable if it doesn't have any proper subsheaves of larger slope. is mu H semi-stable if for all E in F of smaller rank, say, right? Let's say of smaller rank, you have that mu H of E is less than or equal to mu H of F. And then you see, if you don't allow equality here, you call it stable. And if you allow equality, then you call it semi-stable. Okay? So now if you go back to P1, right, if you want something to be semi-stable, right, then A has to be 0, right? Because the moment you have something like O of A plus O of minus A and A is not equal to 0, then you see that O of A is a subsheaf with larger slope, and so it's not semi-stable. Okay? So this kind of, and on curves, this is the notion that you use to get moduli spaces. It's a little bit crude on surfaces. Okay? So what you need to do is you need to improve it a tiny bit. And so there is another notion. So let me introduce that notion as well. So I say that the pure dimensional sheaf. So say that you have a sheaf F, say that it has pure dimension D. And let me point out, you see, this notion depends on the ample that you chose here, right? In my very definition, I had the ample, and this notion will depend on the ample I choose as well. So if you have a pure dimensional sheaves, and then you can look at the Hilbert polynomial. So this is by definition is the Euler characteristic of F twisted by MH. Again, it depends on this ample that we fixed, right? And since it has pure dimension D, this thing starts as AD times M to the D over D factorial, then plus it has lower order terms. Okay? Then it will have AD minus 1, M to the D minus 1, D minus 1 factorial, and so on and so forth, yeah? And so you associate to this sheaf the reduced Hilbert polynomial. And what you do is you just divide the Hilbert polynomial by this AD. So it's denoted by small f. Luckily on the board, big F and small f are completely indistinguishable. So, so this is simply the big F divided by this leading AD. Okay? And again, you have a similar notion of stability. So you call F as Gieseker semi-stable, F as. And if you want to remind the audience that it really depends on age, you call it H Gieseker semi-stable, right? F is H Gieseker semi-stable, even though one usually drops this H because you fix it. H Gieseker semi-stable. Oops, sorry. If for all, again, subsheaves E, proper subsheaves E, you have that, instead of the slope, now this reduced Hilbert polynomial has to be P at PE of M is less than or equal to PF of M. Again, depending on whether you're talking about stability or semi-stability, you allow equality or not, for all M sufficiently large. So you say that two polynomials, one polynomial is bigger than another polynomial if it becomes large enough. So, when you're talking about surfaces and you have torsion-free sheaves, right, what this does is that, then this polynomial starts as the rank times m squared over 2, right? We are dividing by the rank, so the m squared over 2 is always the same, so that part doesn't matter. The coefficient of m is just the slope in that case. So then you see this is a refinement of slope semi-stability by where you look at the constant term of this. So if the slopes were equal, you break ties. Okay? And then the big theorem of the 70s. So this theorem due to Gieseker and Maruyama. Gieseker and Maruyama says that there exists a projective moduli space. Moduli space M, X, H, V, parameterizing S equivalence classes. I guess of H B secure semi-stable sheaves with Chern character V. Okay. It can be empty. Okay. I'll get to that. Okay. But you know, so the one thing that I didn't tell you, what is S equivalence? S equivalence is the following things. So you see, if you have semi-stable sheaves, yeah, so it might not be stable. It might be, you know, it might be extensions of semi-stable. You have a Jordan-Holder filtration. So you call two sheaves, two semi-stable sheaves, S equivalent if they have the same associated gradient. Or in other words, if the Jordan-Holder factors are the same, up to some reordering. Okay?
The graduation are the same.
Say that again.
The filtrations can be different, but the graduation is the same.
Or I mean, yes, the associated gradient is the same. Or if you look at the Jordan-Holder factors, the stable factors up to some reordering, they are the same. I mean, as a multiset. Okay? All right. Okay. So then you see the question that you face is that, I mean, what is the geometry of the space? The space is the main question. So let me tell you, there are a lot of open problems here. So already Leticia was pointing out, so you know, some open problems. And the first problem that you run into is, when is the space even non-empty? When is MXHV non-empty? Okay? You see, these sorts of problems have two types of answers. Okay? Either you can make some assumption on the Chern character, or you make some assumption on the surface. Yeah? And then we have good answers in those two cases, and then in general they are open. So let me maybe discuss this a tiny bit. So let me introduce two things. So we'll talk about the total slope. I already introduced mu h, and this will be new. This just will be a cohomology class. It will be the first Chern class of the vector bundle, or the Chern character, if you want, divided by the rank. Okay? And let me introduce the discriminant. And the discriminant is going to be denoted by delta, and it will be a half mu square minus Q2 over the rank. Okay? This is just a different way. I mean, you know, if you have the rank, the first Chern character and the second Chern character, this data is equivalent to the data of R, nu, and delta. Okay? So if I wanted to know the first Chern character, you know, you take your nu and you multiply by the rank, so you recover this. And then once you know this and the rank, then you know you can determine the second Chern character by just solving it. It's just that very often this coordinate system will be more useful than this coordinate system. So, I mean, the advantage of this coordinate system, these are if you want the logarithmic, the logarithm of this one if you want. It has the property that if you take tensor products, then they add. Okay, that's the good thing about this coordinate system. A lot of times we want to take tensor products in this game, and it's very annoying to work out the tensor product in terms of these coordinates. It's very easy to do it in these coordinates. And the downside is that occasionally we want to take direct sums. And in that case, actually, these coordinates are better than those coordinates. So maybe we'll use both coordinates interchangeably as we go along. Okay? All right. So Donaldson's philosophy is like this. So there's the philosophy of, so maybe I should start here. So there is a very general restriction on when this thing can be non-empty, and that goes by the name of the Bogomolov inequality. Bogomolov inequality. And it says the following thing. If you have a slope semi-stable thing, if f is a slope semi-stable, and it doesn't matter what HIU, sub-semi-stable sheaf, then Bogomolov tells you that this discriminant has to be non-negative. Okay? So that's one restriction. You know, if the discriminant of this B is negative, then you have no hope, then that space is empty. Okay?
But there's no different on it. I mean,
Certainly, well, okay. So you see, in some sense, this is sharp because, you know, line bundles have discriminant 0. If you think about this formula, right, a line bundle has discriminant 0. So, as Laetitia is pointing out, in some sense, this inequality is sharp because for line bundles, it's achieved that you get 0. But that's not a good thing to think about. What you should think about is that you fix a slope. And very often it can happen, depending on the surface, that the discriminant has to be much larger. And it typically depends on what age is for there to be a semi-stable sheaf, and we'll discuss this to a certain extent on some surfaces. Okay? So another way you can ask this question is that the question that you can ask is that what are sharp Bogomolov inequalities? And what Laetitia is pointing out is that if you have that the slope is an integer, right, then this inequality for slopes of stable sheaves is sharp because, you know, you have the line bundles and you can do certain elementary modifications to get slope semi-stable sheaves. Even for Giesecker semi-stable sheaves, you have to think it's not true. Okay? All right. So that's one restriction. On the other hand, there is something called Donaldson's philosophy. Again, I mean, I'm not telling you, I'm not telling you why these spaces are important. Maybe I should have taken some time to do that, but, I'll take it as since you've traveled, 1,000 miles to get here to hear about this, you believe that these spaces are important. And maybe we'll discuss a little bit why these spaces are important. But, certainly they played a big role in Donaldson's four manifolds invariants and things like this. And Donaldson's philosophy is that, these spaces can be pretty badly behaved. On the other hand, if the discriminant gets sufficiently large, then the geometry of MXHV should be nice. And then there are many theorems here that sort of verify Donaldson's philosophy. I mean, there are many names here: Jun Lee, Giesecker, Donaldson himself, of course, Giesecker, and many names here. But maybe the theorem that I should say it is due to O'Grady, which says that if delta is sufficiently large, and he'll tell you some explicit how large it has to be kind of thing, but let me not worry about that kind of thing. If delta is sufficiently large, then this MXHV is non-empty, irreducible, normal, a bunch of the expected dimension and so on and so forth. No, it will be singular. You can't, it can be singular, so you can't quite make it non-singular. That's too much to ask for. Okay? All right? The way you should think about this is that, no matter what the surface is and no matter what age is, if you make the discriminant sufficiently large, then the space looks nice. Okay? Then, of course, the other type of answer you can give to this kind of question is that when the surface is special, right? If X is P2, at some point I'll tell you the complete classification of when that's not empty. If X is a K3 surface, this classification is complicated. It turns out the K3 surfaces for these kinds of problems are usually the easiest. If X is a K3 surface, basically the theorem is, again, due to many people, to Mukai, O'Grady, and a bunch of people, Hoiberg, like large Yoshioka, and the statement is that, the moduli space is non-empty whenever you expect it to be non-empty. Okay? So in this case, MXHV non-empty if and only if the expected dimension is non-negative. I will discuss that. That's fairly complicated, and it's a recent result actually of Jack and Mary that we can completely classify when this thing is non-empty no matter what the answer. Rational rule. Okay. The expected dimension is non-negative. Okay? And again, so on reckless surfaces there is a quite developed classification. Again, certain Del-Petzo surfaces, anti-canonically polarized. When H is the anti-canonical and X is a Del-Petzo, there are lots of results and so on and so forth. Okay. So that's one kind of question. But once you decide when it's non-empty, you can ask more interesting questions, like, for instance, what is the birational geometry? What is birational? Abelian surface also is known the same. X abelian surface. Again, there the theorem is, I mean, the point in those kinds of cases is that the deformation in those cases are fairly simple because they are hyperkähler or sufficiently close to hyperkähler manifolds. And then, you can use deformation theory in those cases to tell when they are. So there's a lot more structure in these two cases. I mean, yeah. Okay. In fact, more is okay. So I realized that I forgot to say something important. So let me maybe go back and say something very important. Yeah, I've been talking about this thing without giving you any examples. I should give you at least one example. What happens when the rank is 1? Right. Then I'm talking about rank 1 sheaves on the surface, right? Such a thing is a line bundle tensor an ideal sheaf of points. Yeah, so what you can do is you can take the double dual of the sheaf, right? If I take the double dual of the sheaf, it will be locally free, so it will be a line bundle. And then, a sheaf includes into a double dual, so you have the line bundle, and then the co-kernel will be supported with a bunch of points, so that you see that in the case of a rank 1 sheaf, this is a line bundle tensor an ideal sheaf, right? So in other words, you can view such a thing as basically as a Hilbert scheme of points on the surface. I mean, of course, if like pick not of the surface is non-zero, then it will be like fibered over an abelian variety by Hilbert schemes of points. But in case you are in the case of a P2 or a K3 or something where the Picard variety is not very interesting, then you see in that case if Picard rank, if pic x is like ZH for some H, right? Then in that case, you have that this moduli space 1, nu delta, if you want, is isomorphic to, a Hilbert scheme of points. So in that case, like the non-emptiness and things are known, the geometry is known much better because we understand the Hilbert scheme of points really well. And occasionally I will use the Hilbert scheme of points to give examples. So I should have said that earlier. Okay, but as I said, once you've decided whether the space is empty or not, then you can ask more interesting questions like, what is the birational geometry of the space? And again, that can mean many different things. You can ask for its Kodaira dimension, you can ask for its ample cone, you can ask for its effective cone, you can ask, what kind of maps it admits to projector space, and so on and so forth. But you can ask other questions like, what is the topology of the space? What are the Betti numbers? What's the order characteristic, and so on and so forth. I don't think that I'll have much time to discuss question 3, but hopefully we'll say a few things about questions. Okay? But when all is said and done, right? At the end of the day, the main question that you face when you want to understand the geometry of a space like this is a cohomological question, right? So the kind of question that you want to know is that if you take some sheaf in this moduli space, many of these problems, if you take a sheaf, and let's say that it's general, right? I saw that, there are other questions that you can ask. When is it irreducible? What is its dimension? And so on and so forth. Those are all questions that you should ask. But at the end of the day, the kind of question that you run into is that suppose you take a sheaf in this moduli space, and let's say it's general, right? Then the question that you want to know is what is the cohomology? What is the cohomology of that? Okay. All right. So maybe let's try to look at a few examples before we go on, right? Again, let's look at the rank 1 case, maybe, just to see what happens. Rank 1. And again, I said that the rank 1 sheaf is going to look like the ideal sheaf of points tensor some line bundle, right? So then you see you have an exact sequence, right? And this is just a set of points, right? So then you have the standard exact sequence that, L tensor IV maps to L tensor OZ, right? So then you see that the long exact sequence will not be associated to this. You see that H0 of L goes to H0 of L tensor OZ. Then here you get the map to H1 of L tensor IZ goes to H1 of L goes to 0. And here you have H2 of L tensor IZ is isomorphic to H2 of L. Right? So, at the end of the day, H2 of the sheaf will just be H2 of the line bundle. And maybe let's put this term here as well, L tensor IZ, mapping to this, right? And then you see if Z is a general set of points, this will have maximal rank. Right? So that you see if the number of points is more than H0 of L, then, this guy will be 0. And if it's less than H0 of L, this map will be surjective, so that H1 of this sheaf will be the same as H1 of that. Yeah? So this will just have, this map will either be injective or surjective. Yeah? So, in other words, in order to understand the cohomology of a sheaf like this, it's enough to know basically what the cohomology of the line bundle is. And depending on your point of view, that's either a trivial problem, you can declare that you know how to compute the cohomology of a line bundle on the surface, or it's an impossible problem, right? For instance, if you have P2 blown up at 10 points, right? 10 very general points, we don't know when a line bundle has any sections on such a thing, for instance. So, But anyway, we are not going to answer what the cohomology of a line bundle on a surface is. You either know it or you don't. So, depending on what surface you're working on, what situation you're working on, it's either easy or it's impossible. So, okay. In any case, if you have a rank 1 sheaf, at the end of the day, it's just the cohomology of the general one, where this Z is a general set of points, just boils down to the cohomology of the line bundle. So let's do just a pretty concrete example here. Yeah? Let me just take IT of -3 on P2. Okay? So this is just one point on P2. P is any point on P2. This is the, I twisted by -3, right? So what's the Euler characteristic of this thing? It's 0. But you see, the problem is that the cohomology doesn't vanish. Right? The cohomology of this thing is that both H1 of IP of -3 and H2 of IP of -3 is just one-dimensional. They are both C. I mean, it follows from what I told you here, like, H2 of IP of -3 is H2 of O of -3, but O of -3 on P2 has one H2, so this has one H2. On the other hand, it doesn't have any H naught, right? Already O of -3 doesn't have any H naught, right? So you're just, since the Euler characteristic is 0, then H1 has to be 1 as well. So, okay? So you see already that, if I want to find, right, the cohomology of a sheaf, of the general sheaf, and this is the general member of this moduli space. Every member of this moduli space looks like this. So they all have an H1 and an H2. So you see, it's not enough to compute the Euler characteristic and declare that, okay, I know the cohomology. The perfect world would be that I would give you the Euler characteristic, and from that, you could tell me what the cohomology is, right? I mean, that's the whole point of Euler characteristic, at least for the general sheaf. And this is telling you that, okay, you have to be maybe a little bit careful, okay? And it turns out that this is the only thing that goes wrong on P2. Okay, what? No, for any rank. So like the theorem is like this. So this is go to Izzet. And it says the following thing: let F in MP2. Well, I mean, there aren't really any choices of MP and MP2. There's only O of 1. Let me just put that out. That's the class line of the classical line. B. Well, okay, let F be a general sheaf, and assume okay, so that I exclude this case, right? Then the statement is that then F has at most one non-zero cohomology. So where? This one? This was completely general. This is any surface. I mean, this example, I just gave it on P2 to be concrete. If you take any line bundle with H2, like, you can add some points to it, it will have both H1 and H2 eventually.
But that would be in any surface.
Yeah, this is okay. Yeah, sure. This kind of example you can make on any kind of surface. I just want to just give it a concrete one. Okay? But this theorem is very much P2. I mean, here it's very important that this is P2 and this is important. Otherwise, I give you a counterexample. Okay? So maybe what I want to do is I want to sketch a proof of this thing so that you see like what goes into proving something like this. Okay? And then, the main thing so what's the difference? Why does it work in this case and it doesn't work in this case? The difference is that you don't have Serre duality in this case. Yeah, whereas you have Serre duality in this case, because the general member of any moduli space on P2, the moment the rank is at least 2 is locally free. So the main difference between the counterexample and the theorem is the failure of Serre duality. So maybe I should make a remark, yeah? Failure of Serre duality. Serre duality is the main culprit that makes the example work. Is what makes the counterexample work. And this will be, a general kind of annoyance that comes up. It can happen that you have moduli spaces on the surface, even of high rank, such that the general member is not locally free. So we can add to our questions here, to our open problems, if you want. When is the general member locally free? We don't know that in general either. And it is part of the theorem for graded that the general member in such a moduli space is actually locally free as a bundle. Okay? Okay? All right, so let me sketch this. Maybe I'll explain eventually why the general member is locally free. But let's pretend that we know that for now. Okay? So let me make so let me just use Serre duality from the very beginning. Use Serre duality to assume that the slope, it's the L slope, let me just write it like this, is bigger than or equal to minus 3/2. The canonical of P2 is minus 3. So, so you can always, by Serre duality, make the slope greater than or equal to minus 3/2 by passing to the Serre dual. And, if you know that the general member is locally free, then in order to compute the cohomology by Serre duality, you might as well compute the cohomology of the dual. Okay? So let me do that. Okay, so here's what I want to do. The thing that you have to understand is that it's, in general, very hard to make a stable bundle. And it's also close to impossible to check whether any given bundle is stable. There are exceptions, but you have to make it contrived in order to, there are instances where you can check because numerically somehow everything else goes away. But in general, if I give you a random bundle as a presentation of, I give you some co-kernel or some map of bundles, you understand, or line bundles or something like that. It's close to impossible to check that it's stable. And there are cases when you can do it, but it's not easy. Okay, so what I want to do is I don't want to think about stable bundles at all, and in fact it turns out that the theorem is not a theorem about stable bundles. Okay, so the definition is, let's make this definition maybe in general, right? A sheaf, again, sheaf, sheaf again means coherent and so on and so forth. A sheaf on a surface X is D prioritary. And D here is some divisor on surface X. This is D is a divisor on X. If the following thing happens, if X2, let me say effective divisor if you want. D is an effective divisor. If X2, a sheaf, let's give it a name, sheaf F minus D is 0. Okay? Some condition like this. X is a surface, D is an effective divisor on X. And you can make it a line bundle if you want to, but anyway, it's the same definition. So I'll call it D prioritary if X2 of FF minus D is 0. Okay? So now, let me explain a little bit why we care about something like this, yeah? Yeah, so you see what this means is like this. It means that the Kodaira-Spencer map of from the deformations of F on the surface to the deformations, the restriction of F to D is surjective. So if you write the long exact sequence, you get X1 FF going to X1 F restricted to D, F restricted to D to this X2. the fact that this x2 is 0 means that that Kodaira-Spencer map is surjective. So the way to think about this is that the deformations of f on x surject to deformations of f restricted to d on d. Okay? That's how you should think about it. All right. And then why do we care about this condition? There is a theorem here that's worth mentioning. So let's start with that. So the theorem is due to Walters. And it says the following thing. Let X be a birationally ruled surface. Okay? What that means is that there is a map from X to a curve, and then the general fiber is a P1. Of course, to say this birationally ruled, it's not quite ruled. Some fibers might be a bunch of P1s or something like this, but the general fiber is a P1. Okay? So maybe let me. So that the general fiber, this is a curve. The general fiber is a P1. Okay? So you start with a birationally ruled surface. In particular, there's a fiber class, the general fiber. So then it says the following thing, the stack of F prioritary sheaves. Let's make it like this, F prioritary sheaves is irreducible if non-empty. Okay?
Sorry, the definition is for any D, or there exists a D?
No, you fix your D.
Okay.
I fix my D. So I talk about prioritary sheaves with respect to that D. And then in this case, I fix the fiber, F, the fiber class, the general fiber. So I want to talk about the sheaves that are F prioritary.
With respect to that D.
With this F, with respect to F, with respect to the fiber. So in other words, I look at sheaves F, X2, maybe F is an unfortunate choice. This F is the fiber class of the surface, or fixed general fiber.
But F is the same as
F is the D, yeah. This F is the D, yeah. But I don't have to define it with respect to such a fiber. I could do other things, and I will eventually. So that's why I give you the general definition. But yes, so here, F take D equal to F in the definition. Okay? All right? And you can imagine how to prove this theorem, right? I mean, the way you prove this theorem is that, I'm not going to prove it for you, but you use the fact that now you see the deformations of this sheaf on the surface, right? Surject the deformations of this sheaf to the restriction to the P1. But we understand the deformations of a sheaf on P1. Any bundle on P1 is a direct sum of line bundles, and the general one is as balanced as possible. So then you see, because this is a one-parameter family like that, so you can assume that actually they are either all balanced, or if they are completely balanced, then they just become unbalanced by one, right? And then so you see, in other words, you see that stack is basically smooth at points like that. And then, to say that this is reducible, you need to say that it's connected, and then, you know enough about the geometry to just do it, okay? Basically, you can use the Balanced spectral sequence to completely classify what these things look like, and so on and so forth. I'm not going to prove this, but, it's a theorem.
And there is some property for the F of the D of the divisor. I mean, the divisor has to have some extra.
No, but let's answer your question now, okay?
Yeah.
This is a good question. So far, this is just something about some prioritary sheaves. In particular, you see there was an earlier theorem due to Hirschowitz and Laszlo that proved the same theorem just for P2 with F equals L. Okay, but you recover. Okay. So the theorem for P2 was due to. So this was first proof for P2. For P2 by Hirschowitz and Laszlo. Okay. All right. So now let's answer Letitia's question. Why do we care about this thing? So think of it like this. So now say that age is an ample. Suppose age is an ample such that h dot kx plus d is negative. Okay? This doesn't have to happen, but sometimes it happens, right? So then the claim is that every H semi-stable sheaf is d-prioritary. Okay? So in particular, you see this moduli space of semi-stable sheaves sits in this prioritary sheaves, and as in, if you look at the stacks, as an open substack. So if this thing is irreducible, in particular, the moduli space is irreducible. So and why is this? It's a simple calculation, so we might as well do it. Question? No, feel free to interrupt me whenever I don't make sense. Let's see. So you see, I want to compute x2 of f minus d, right? But by Serre duality, this thing is the same as Hom, f kx plus d dual. Yeah? But you see, what I said is that the slope of f, the h slope of f, is strictly less than the h slope of f kx plus d, right? By an assumption, because this h dot this kx plus d is negative. Yeah? So that you see that this is zero. There can be no homomorphisms from a, semi-stable sheaf of which way? Yeah. You can't have like, if you have a semi-stable sheaf here and then you have a map to a larger slope thing, then you see then the kernel would be destabilizing. So this guy is zero. So that you see that you're deprioritary. So you see that this notion is very useful when kx is somewhat negative. So on things like P2 or rational ruled surfaces, this will be very useful. It's completely useless, of course, if you want to talk about stable things and kx is positive. Even if kx is zero, then you don't get much mileage out of it. But for our discussion today, when we want to understand the cohomology for things like P2, it's very useful because, instead of thinking about stable sheaves, I can talk about prioritary sheaves. And this condition is much easier to check than stability. That's what I gain. And the extra thing I gain is that I also know that, under certain circumstances, the stack is irreducible. So if I want to compute the cohomology of something and say that the cohomology vanishes, it's enough for me to exhibit one prioritary sheaf where the cohomology vanishes. Then by irreducibility and openness of cohomology, then, upper semi-continuity of cohomology, I get it for the general one that vanishing happens. Okay? So those are the two advantages that I get. The first advantage is that I replace myself with an easier to check condition. The second is that, because I know that this is an irreducible thing, then I can exhibit to you just one where the cohomology vanishes. Okay, let's put it to use. So now that we have this little machinery, let's prove the theorem. Okay? So the first thing is that let's look at something like this. I look at O of A to the n plus O of A plus 1 to the R minus m. M is some number between 0 and R. Okay?
I guess you still, I'm sorry, I guess you still can have there are a whole bunch of
Sure. Yes, I mean, there can be a lot of priority sheaves, and none of them may be stable. That's absolutely true. Right, the stable ones can be empty. I mean, it's an open substack, but remember, when open things can be empty, and the empty set is an open set. Okay? All right, so here is an example to answer your thing. Like, look at something like this on P2. Okay? So now what we are doing is that I'm sketching for you a proof of the theorem of Goethe and Hirschowitz. Okay? So let's look at something like this. It's obviously not stable. I mean, unless M is 0, it's not semi-stable, right? I mean, you know, this part is a positive sum, more positive than the whole thing. But the whole thing is this L priority. This L priority, O of 1 priority. Right? If I wanted to do x2 of, so you know, if you wanted to compute x, you know, and of a minus 1 plus of a r minus m, right? This guy is 0. Simply because, you know, h, you know, O of minus 2, O of minus 1, oh, don't h2, right? You know, the worst case is when this happens, right? For these two players, in which case you're computing h2 of O of minus 2 and it's still 0. Okay? So that's when you gain. You know, this thing is clearly not stable, but it's priority. And you know, it's not hard to check this thing. I mean, you know, this you can put on your, whenever you're teaching Hartshorn, you can put it on the exam. In fact, I think I did this semester.
So the complexity is the interesting part. I mean, you can prove that there are no stable sheaves. You prove that there are no...
Absolutely, and we'll do that.
That's a very interesting way to...
Yes, you can do that. We will do that, in fact. Yeah? Right? I mean, you know, if you can prove that there are no priority sheaves, right? Like, that, like, you know, assuming that D satisfies this inequality, then it follows that there are no semi-stable sheaves either. And in fact, that will give fairly sharp Bogomolov inequalities on rational ruled surfaces. You'll see in a second. Okay?
Yeah, because you get that inequality.
Right. Yeah. Okay, so but here is, like, you know, and notice that I can make any slope that I want, right? Given the rank as slope, then I can make any of them by like this, yeah? So you know, so remember we said that our slopes that we are trying to make are bigger than minus 3.5, right? So notice that I can get any slope this way, right? I mean, you write your slope as C1 over the rank, right? You do the division, you get some A, and then some remainder. The remainder is R minus M, and you know, the A is the quotient, so that you get any slope you want like this, okay? You don't get all discriminants, of course. You just for each slope, I gave you one discriminant. Let's compute the discriminant. Maybe let me not compute the discriminant, but the claim I make is that the discriminant is less than or equal to 0 of this thing. Again, I mean, you know, this isn't a deep thing, you know. This is, you have the slope square minus, you can compute the Q2 of this thing divided by R. The discriminant is less than or equal to 0. So in particular, you see many times, if it's not just one factor, the discriminant will actually be negative. So you have a priority sheaf, and clearly you don't have any semi-stable sheaves by Bogomolov. So that's an example for what you asked for. Okay, good. And notice that in the range we want, A is greater than or equal to minus 2, right? Because, I mean, we want the slope to be bigger than or equal to minus 3.5. So that you see that these bundles have no H1 and no H2. Okay? All right, so far so good. So they can only have H naught. All right, but how do you get all the discriminants? I mean, so far this doesn't do what we want. So here is the next technique that maybe we should talk about, and that's elementary modification. So I do elementary modification. And here is what it says. So here is what you do. You say you have a sheaf. You take a general surjection to some OP. Okay, you take a general point on your, this again doesn't have to be on P2, on any surface. You take a general point in the general surjection, and then you have a kernel of this. So this V prime is called an elementary modification of V. Again, you see, if this is really a general map, then a few things are easy to check. If V is D priority, then V prime is D priority. So if V is D priority, then D prime is V.
For a general or?
Yeah, for a general one. D prime. Again, I take this to be general. Okay? I mean, it's also true if it's slope stable or slope semi-stable. V prime is slope stable and V prime is semi-stable. What happened?
If V prime is the priority, then V is the priority.
I don't know what that means. If you're given V prime, what do you mean by V? Sure, and you can take the double dual, but so it will be a sequence of elementary modifications. I believe so, but let me think about that. Okay. And again, if V is slope stable or slope semi-stable, V prime is slope stable and slope semi-stable, but that's false for Gieseker. Yeah, it's if V is Gieseker stable or Gieseker semi-stable, V prime doesn't have to be Gieseker stable or Gieseker semi-stable.
It's very general,
no? Really not. Here is an.
The slope is the general. Otherwise, doesn't.
No, actually, as
general stable bundle, you need.
Well, I mean, Gieseker is false even when you take general. Okay? I mean, if you want an example, think of the following. Example, take P2, yeah, and take O plus O for V. Then if you do one elementary modification, there's simply nothing that's Gieseker semi-stable on that. Okay? I mean, you can do it with Gieseker stable too. This is a little cheating because it's semi-stable, but you can even do it with stable. Okay? Anyway, this is the easy example. Okay, so this was supposed to be an example. Elementary modifications don't preserve Gieseker semi-stability. Okay? They preserve slope semi-stability and slope stability, but not Gieseker semi-stability and Gieseker stability. So you have to be a little bit careful. But they preserve prioritariness, okay? The other thing is that what happens to the cohomology? What happens to the cohomology is that if V has H naught, then V prime has one less H naught, and H1 and H2 don't change. And if V has more H naught, then V prime has one more H naught than V, and H naught and H2 don't change. Okay, so H2 of V prime is equal to H2 of V, and the map is has maximal rank by the fact that you chose it to be general. Okay, and plus let me say it like this: if V has only one non-zero cohomology group, one non-zero has at most one non-zero cohomology group, then so does V prime. Okay? If V has only H naught, then V prime has one less H naught. If V has only H1, then V prime has only one more H naught. That's just by the same exact sequence, basically. Okay? All right, now we're done. Yeah. So I've constructed for you priority sheaves for every slope and discriminant less than or equal to 0. Maybe one other thing that I should say, like, you know, like each time you do elementary modification, you increase delta of V prime is delta plus of V plus 1 over R. And this way you hit all discriminants because, you know, by integrality of the Euler characteristic, you know, there can't be any discriminants less than 1 over R apart. Okay? This is by Riemann. Okay? So, say that again.
H0 V prime.
H0 V prime is 1 less than H0 of V unless H0 of V is 0, in which case. Okay?
So it's increasing by 1 over.
So H naught keeps dropping by 1 until it becomes 0. As you make elementary modifications, general elementary modifications, H0 drops by 1 until you get to 0, and then H1.
Look at it the other way. I mean, you start with V prime.
Yeah?
And then you construct V, and then you are increasing 1.
That's right. You want to increase it, then you will be increasing. That's right. But as usual, I mean, I don't think that that's a meaningful way to go.
Yeah, the thing is to prove the stability of them.
That's right. Okay, but now we're done, right? Because for discriminant less than or equal to 0 and all slopes, I gave you a bundle that has at most one non-zero cohomology group, and then you take as many elementary modifications to get the priority sheaves with the same property. You hit your Chern character, yeah. That bond, once you make enough elementary modification, you've hit that Chern character. It still has at most one cohomology group, and that stack is irreducible. So the general member of that has at most one non-zero cohomology group. That's the proof. Okay, it's fairly simple actually at that. Okay. All right. I'm going to give you some more consequences of this in a second, but maybe let's go to the next complicated surface. Okay?
I was about to ask.
All right.
I have a question.
Yeah.
If I just look at the cohomology sequence,
Yeah.
let me assume, for instance, that V doesn't have H1.
Yeah.
Why can't it be that it runs the same number of sections, but one?
Because you see, we took a general elementary modification, right? What that means is that the map from H naught of V to H naught of this, which is one dimension, is surjective. Right? So in particular, H naught of this has one B to the one less than that. I mean, it's important that I'm taking a general one. I mean, so another way to think about it is like this. Take your section, right? It's easier to see it sometimes like this. Take your H naught of V, pick your favorite section. You know, then it doesn't vanish at some point. It's not something from hyperpolymorphism. And that's the elementary modification you take, and that's still not. Right? The general one, then it means that it has to go down by one. But that's a good, I mean, like what I'm saying here depends on this being general. Okay? Sure, I mean, you can take like, if all the sections are vanishing at some point and you try to do an elementary modification at that point, of course, then it won't work. Okay? Yeah. Okay, so let's just maybe move on to the next surfaces. So is this good? I'll come back to P2 and give some more discussion of this. But let me maybe say the theorem. So on P2, the only thing that could fail was Serre duality, and that happened for rank 1. So now let's look at Hertzberg surfaces, or rational rule surfaces. So these are the surfaces that are given as the physical equation of all plus OP1 of E. And I'll call this thing F. Okay, E is still some integer greater than 0. Okay? So a few things about these surfaces, you know, they have a natural projection to P1. Then, you know, the Picard group of this FE is generated by ZE plus ZF, where this F is the fiber class, fiber of pi, and this is a section of pi. With half intersection y. Okay? Can I assume that people have seen the surfaces before? Should I say more? I see people nodding, so I'll assume no. Okay, let's say a little bit. So if E is 0, okay, this thing is just P1 cross P1. Okay? If E is 1, then this thing is the blow-up of P2 at the point. Okay? These two surfaces are hopefully familiar. Then you see, if you want to create the other ones, right? The way you should think about it is that I have this special section, right? It's fibering over P1, right? And say that this is FE. If you want to go to FE plus 1, well, you do an elementary modification. What you do is you take a point on your end, it doesn't matter which one, you blow it up. Let's blow it up. So we blow up. So let's call this point P. It's on the special section E. You blow up FE like this. Then here is the picture. So I get a new E, right? Now the south intersection, this one was minus E. If you blow up a point, it decreases by 1. So now the south intersection of this new guy is minus E minus 1, right? And then you see here there was a minus 1 curve and the exceptional divisor minus 1 curve. Let me maybe, I have some yellow chalk here, let's make the exceptional divisor yellow. Okay, that's the minus 1 curve, that's the minus 1 curve. So now you see by Castelnuova's theorem, I can choose to now contract this one as opposed to that one. If I contract this minus 1 curve, I'll go back to the original surface. If you contract this curve, you come to FE plus 1. Where you have this new E with self-intersection minus E minus 1, and then you're going to some other fibration to P1. Okay? The way you can think about this is that you do an elementary modification on this, on this bundle, and you go from the O of E to O of E plus 1. Okay? So that's the surface. At least, you know, the first few are familiar, and then, you know, the way you can go from one to the other pretty concretely. Okay. So now you see, the problem before on P2 was that, you know, we had non-locally free sheaves occasionally, and they cause some trouble. But here, like, let's look at this. So here, the new problem that you face. And again, when I say problem, okay, so let's go back. So in particular, you see, if you have a modular space of sheaves rank at least 2, right, then the Euler characteristic and the slope completely determine the cohomology of the general sheaf, right? So if the Euler characteristic is negative, you only have H1. And if the Euler characteristic is positive, you can have H0 or H2. And which one you have is determined by the slope. If the slope is less than minus 3 halves, then you have H2. And if it's more than minus 3 halves, you can only have H0. So it's not a completely numerical thing on P2 to tell you the cohomology of the general sheaf. So that's the dream situation, yeah? Right, that's what we proved.
Wait, that argument doesn't really depend on the polarization.
Yes, this argument doesn't depend on the polarization. And also, you see, we proved a much more general theorem. What we proved is that if you have a priority sheaf of discriminant at least 0, then, you know, the cohomology of the general sheaf can be at most one thing. It had nothing to do with stability. Okay? I don't need to know stable sheaves to prove the theorem on P2. It's more general than the, you know, Goethe-Hirschowitz theorem. Okay, so the new problem that you face when you go to a surface like this, you see there are these negative self-intersection curves. Negative self-intersection curves. So, here is what can happen, right? Let's look at, chi of, so let's look at, for instance, O of E, right? So typically the chi of this is going to be negative. I mean, as soon as E, I think, is bigger than 2 or something like this. I mean, let me tell you what the chi is. So, if you have AE plus BF, then, you can use Riemann-Roch to compute the chi of this thing, and I think it's A plus 1 times B plus 1 minus E over 2 times A times A plus 1. This is just Riemann-Roch on surfaces. So that you see, if your B is 0 and, your A is 1, then you'll get something like 2 minus E over 2 times 2, right? So you'll get 2 minus E. So as soon as E is bigger than 2, you'll get a negative number. So chi of O of E is negative, right? But of course, this thing has H0, right? This E is an effective curve, right? So you see that both H0 and H1 of this thing are non-zero. So H0 of O of E is one-dimensional, and H1 of O of E is non-zero because the chi, so you see if E is bigger than 2, so we get that this chi is.
But when you have the negative self-intersection curves, you can always contract and go to the middle.
You can, but then the surface becomes singular. Yeah? Yeah. Yeah, I mean, it's a cone over the rational normal curve of degree E, right?
Yeah, because I mean, what I don't understand is that you go to the minimal model,
No, these are minimal. I mean, and as long as E is not 1, the surface is minimal.
Yeah, but if you have self-intersection curves, then you can contract them.
You can contract them, and in that case, you get the cone over the rational normal curve of degree E in this case. Yeah? So some singular. I mean, you see, the bundles don't need to descend, yeah?
Okay.
Right. Okay. So in other words, you see that the existence of this negative self-intersection curve. In other words, let's put it a different way. So it can be that chi of F so here is what can happen. Chi of F is negative, but chi of Fe is positive. Okay, it can happen. It can happen. That chi of F is negative, but chi of Fe is positive. For instance, if you had something like, what's an example of such a thing? So in particular, you see if there is a section of F, the other way around, sorry. It can happen that this is positive and this is negative. So like the example here is that, for instance, if I take F to be O, right? Then chi of O is positive, it's 1, yeah? Whereas chi of OE, as soon as E is bigger than 2, is less than 0. So then you see what that means is that if chi of F is positive, you expect sections of this F. And, it will, if H2 is 0, let's say, and, we'll be able to tell when H2 is 0. If H2 is 0, then this thing will have sections. That's how you get chi positive. But you see, you don't expect there to be sections here. But of course, once this has sections, then this has to have sections, right? Because, you have a map from F goes to F of E goes to F of E restricted to E, right? So in particular, if H0 of this is non-zero, H0 of this is non-zero, but it can be that the Euler characteristic is negative, and here is an example of such a thing. Yeah? And then the theorem is that this is the only thing that can go wrong for these surfaces. Okay? So let me maybe state the theorem a little bit more. Say that again? Yeah, the rank 1 we discussed already. The rank 1, it just depends on whatever happens to the line bundle. So here is the theorem. Here I have the statement. So this is the theorem. This is with Jack, if you want. And it says the following thing. So let me assume that the rank is at least 2. The discriminant is greater than or equal to 0. then you have the following statement. Then the stack of F prioritary sheaves let me denote it like this, P, F, E, F, V is non-empty. And now, so if it's non-empty, it's irreducible by the theorem of Walters. So, that's because, so it's so irreducible by Walters theorem. So in particular, so now let F be a general. So let's V in this prioritary be a general sheaf. So you have the following thing. So I look at the total slope of V and I dot it with F. So if this thing is less than or equal to -1, then V has no H0. If this is the total slope dot F is greater than or equal to -1, then V has no H2. So you can tell, first of all, whether its priority sheaf has H0 or H2, depending on just, you look at the total slope, so that will be some rational number times E plus some other rational times F. So if the coefficient in front of the E is less than -1, you don't have any H0. If it's bigger than -1, you don't have any H2. Okay? So in particular, if this intersection is -1, you can only have H1. So that the Euler characteristic completely determines the cohomology. Should I write that, or is this clear from the two? Yeah? So in particular, if you have equal to -1, you don't have H0 or H2. You can only have H1. Okay? So that's the first statement. So by Serre duality, I can assume that this intersection is -1. Again, I assume that the rank is bigger than 2, so that I have Serre duality. So by Serre duality, assume that nu of V dot F is bigger than or equal to -1. In that case, you get nu of V dot E now is greater than or equal to -1, then V has at most one non-zero cohomology group. And 3, if nu of V dot E is less than -1, then you have H0 of V is isomorphic to H0 of V minus E. Okay? Combining all these statements, the remark is that this completely computes the cohomology of the general sheaf on all these things. The remark completely computes. General F prioritary sheaf of rank at least 2 and delta greater than or equal to 0. But rank 1 case we know completely too, because we know the cohomology of all line bundles on the surface. Okay? All right. And again, the proof is the same. The reason I presented the P2 proof like this was not because it was the original proof, but So now the FE proof is the same, yeah? So what you have to do is you need to find a direct sum of line bundles, right, that has a most one cohomology group, and that tiles all the possible slopes, and the discriminant is less than or equal to 0, and you can do that. Okay? So
In this case, the stable bundles are soft.
say that? Yes, they are. The moduli are irreducible always. That's right. The moduli are, are open substacks of these things, and then whenever they are non-empty, then the general stable bundle has no right. Okay, that's correct. That's a consequence of the Walter theorem. All right, so I think maybe we have another, 10 or so minutes. So, so maybe instead of redoing the proof, right? I mean, the proof is exactly the same. You can look in the paper, so how you tile it by line bundles and so on and so forth. Let me talk about some applications with these things, okay? So that you know what kind of applications you can get. So the first application is Gaeta resolutions. So you see, this allows you to get your hand on the general bundle. So now what's a Gaeta resolution? So you see, the easiest thing to see, I think this Gaeta's paper was 1956 or something like this, where he wrote down the resolution of a general set of points on P2. And then, you can see, so on P2, if you have 2 points, or maybe you have 1 point, if you have 2 points, then the resolution is right. If you have 3 points, then the resolution is contained in 3 quadrics, and then there are 2 cubic relations. If you have 4 points, these are general points again. That looks like this, right? It's a complete intersection of 2 quadrics or something like this, yeah. And anyway, you can imagine what it looks like. The thing that you should notice is that only 3 numbers appear here. Yeah? So the theorem for P2 is like this. If you take the general prioritary sheaf, actually, then it has a resolution like this. The general prioritary sheaf, on P2 has a resolution like this. It's O of A plus O of A minus 1, O of A minus 2. And then, there's some alpha, beta, gamma here, some exponents. And it could be that the exponent of beta is negative, in which case you put it on the other side. Okay? And then, there is absolutely no mystery about what A, alpha, beta, and gamma are. A is, the largest number such that f of minus A has H naught, but, one more doesn't have H naught. So, you know what A is. And then, once you know A, then, this alpha, beta, and gamma you can determine by orthogonality relations, right? So, I twist this by O of minus A. So if I twist this by O of minus A, there's an O of minus 2 here, there's an O here, and O of minus 1 here, yeah? So then that alpha is determined by the number of sections of that thing, or the Euler characteristic of that. F tells you alpha. You can twist this thing by minus A minus 1, then you see no cohomology here, there's O of minus 3's here, so the Euler characteristic of that one tells you what that is. And then from the rank, you know what this beta is. So, you can solve for these things. And then you see, this is also a proof, if you want, that the general sheaf of rank at least 2, the general priority sheaf of rank at least 2 is locally free. Because you see, once you know the invariants that give you your V, you simply write this and you look at the generic map like this. It's easy to check that it's priority, and by Bertini, it's locally free. Okay? that was fast, but
So you have a family of general priorities, so you have priorities.
yeah,
On P2, for each one of those, you have a stack.
that's right.
So when you vary the priorities, how the stacks are moving,
Right.
how they are changing.
These numbers will change. The A, the alpha, beta, and the gamma will change. But you see, A, alpha, beta, and gamma are determined by Euler characteristics of F and its twists.
Yeah, so it seems to me that, I mean, for each one of these priorities, you have a stack.
That's right.
And there are the locally free.
That's right.
So when you move the priority, that stack moves, but you also have the locally free shifts.
So on
They're going to be
P2,
constant.
on P2, you don't have a choice for
You
what.
have families of stacks. You don't have. I mean, for each priority, for each divisor that has some such property, you have a stack.
Right, but I mean, you know, the invariants completely determine what happens, right? So if I have, like, if I look at the PP2L of V, right? This V completely determines the A, the alpha, the beta, and the gamma. I have no choice.
The L.
You can't. I mean, L doesn't
Well,
move. It doesn't move.
yeah.
That's right.
So you don't move the V in some sense.
No, it's just, it's determined. But you see also why the, you know, as soon as the rank is at least 2, then the general one is locally free because it's a general matrix like this, right? And you know, Bertini's theorem tells you, Bertini type theorem tells you that you have to be locally free.
This is saying that you can still consider stability and all that as your conic instead of a line.
Say that again?
That you can still consider trilateral sheaves with respect to a conic.
You could. Yeah, you will get the disaster pretty quickly. I mean, you see, I mean, the thing that you consider, conic is still okay, but that's the last time it will be okay, right? Because, I mean, you know, this thing has to be, this thing plus kx had better still be negative.
Oh, that's right.
Right? Otherwise, you're not going to get.
No, I mean,
No, I mean, she wants to do it when pick not is not 0 and move the line bundle.
to get a family of models.
But you see, in those kinds of cases, it will just fiber to pick not. And, you know, the fibers will all be isomorphic, so to speak.
Would you say isomorphic or birational?
Isomorphic, because if you tensor by a line bundle, you'll get an isomorphism. Because, I mean, you can tensor by the inverse line bundle and go back.
Yeah, well, then
It's homogeneous by the group action.
Say that again?
The vibration is homogeneous by the group action on big signal.
Right, but yes. But, yeah, I mean, yeah. Okay. So the first consequence of this thing is that there's also a Gaita resolution for these Hirzebruch surfaces. So again, this is the theorem with Jack. So the general, I mean, so the general F prioritary sheaf admits a Gaita resolution. And then I guess I have to tell you what this resolution looks like. Now it will look like this. You'll have L minus E plus 1F. Actually, it's more canonical than in the case of P2. It will go to L minus EF plus L minus F plus L. Go to your sheaf. Sorry, I wrote this thing like this. And again, you know, you'll have some. Again, the numbers are. Here you have more choices as to what this line bundle can be. You know, but you know, the claim is that there exists a line bundle such that you can get a Gaita resolution of this type for your general prioritary sheaf with non-negative discriminant. Okay. And then, you know, it's crucial that you know that the cohomology vanishes when you prove these theorems, because at the end of the day, these things all boil down to saying that the Euler characteristic is giving you the right, the right things. Now, what are some consequences of this? I mean, should I stop or should I go a little bit more?
You already said it, but can you repeat, please, how do you, so it is clear that from out of the cohomology computations, you get the generators for general sheet P2 or,
I mean, how do I determine what alpha, beta, gamma, and delta are?
how do you get right exactly?
So let me say it again just here, yeah? So suppose that you found what A is, and the A you find is that, it has to be the chi of F minus H naught, sorry. When you do it, you do it with chi. So you look at chi of A, F minus A is positive, but chi of F minus A minus 1 is negative. So there will be one number A where this kind is maybe like this. There will be one number where this thing is going to hold, and that number A, that integer A, is this A. So that determines your A. And once you know what your A is, now you need to find what alpha, beta, and gamma are, right? Well, so let's compute alpha, right? So twist this thing by minus A. Twist this by minus of minus 2 gamma maps to O alpha plus O of minus 1 beta goes to F minus A, right? But then you see that the Euler characteristic of this thing is the same as alpha, because this has absolutely no cohomology and this has absolutely no cohomology. And then similarly, if you twist by minus 1, A minus 1, right? Then here you get O of minus 3 gamma. Then here you have O of minus 1 alpha plus O of minus 2 beta. Yeah, then you go to F minus A minus 1. Again, this has absolutely no cohomology, this has absolutely no cohomology, so the Euler characteristic is negative the Euler characteristic of this one. And then beta is finally determined because alpha plus beta minus gamma has to be the rank. And it could be that it's negative, in which case you have to put it over there. Okay? So it's the same here. I mean, if you think a little bit about the cohomology, it's the same. Okay? All right, so I was going to tell you 2-3 more applications, but maybe I should stop here, or I don't know. Have I exhausted everyone?
The wrong person to ask.
So maybe let me go on for 5 more minutes and tell you some problems and applications. So you see, one interesting application of this thing, which seems to have been missed even for P2. So the theorem is that we cannot classify all Chern characters where the moduli space, the general member, is globally generated. Yeah. So the theorem is like this. Maybe let me first say it for P2. So this was partially proved by Bertram Goller Thomas. Bertram Goller Thomas. And then sort of cleaned it up. So this is on P2, right? So it has the following thing. So you know, the general member, the general sheaf F in the moduli space in P2 is globally generated if and only if one of the following holds. If and only first the slope of F is met, right? That means that, you know, you look at the thing that's greater than or equal to 0. Yeah? And, you know, one of the following holds. Either 1, the Euler characteristic of V is at least R plus 2. 2, 3, the Euler characteristic V is R, and then in that case F has to be O to the R, and the Euler characteristic of V is R plus 1, and you know, there's like 2 pieces. You know, it's basically like the tangent bundle twisted by -1, TP2 -1, there is an exceptional bundle 2/5, and so on. Like, you know, there are like 2-3 cases. It doesn't matter what they are, you can write them all down. They basically all boil down to having a resolution of this form. Okay, these are the only possible resolutions you can write. Okay, I mean, you can say exactly what they are. So the interesting theorem is like this. So I want to know when the general sheaf on P2 is globally generated. And the statement is that basically if and only if the slope is non-negative and it has at least R plus 2 sections. Okay? And then, you know, it could have R sections, in which case your R can R plus 1. So, you know, these two cases are stupid exceptions that you have to worry about. R is the rank. So what this is saying is that I can tell when the general sheaf is globally generated. But let me be careful here. Being globally generated is not an open condition. Okay, so the question that I'm asking, when is the general sheaf globally generated? Okay, so the general sheaf will be globally generated as soon as the Euler characteristic is at least R plus 2. The way you should remember it is like this. And then, you know, there are a few cases when there's R or R plus 1 that you can work out. Okay, and then there's a corresponding theorem for Hirzebruch surfaces. This is now Jack and myself, is that the general sheaf in, say, F in M, I mean, you don't have to be M, you can do prioritary again, FE, FV, let me assume that, you know, the discriminant is greater than or equal to 0, is globally generated if and only if. Again, the total slope has to be NF. There's NF. And again, need to hold. Let me not go flying down. This is the total slope, or this delta, so it's a poorly written delta. Okay? This thing is NF, and, you know, again, I mean, the interesting case is that, again, when the Euler characteristic is, you know, there are some the bundles can be pulled out from P1 and stuff like this that you need to. So let me just say, and one of the following holds. One, either you have that the total slope dot F, this is V, is equal to 0, and then your sheaf is, you know, something AF. And there's some power there, and then this is equal to 0. 2, you have that new V dot F is greater than 0, and the Euler characteristic of V minus F is greater than 0. So the way to think about this, I mean, of course, it could be that even if you twist this thing by minus F, then your Euler characteristic is positive, so that you have H0. And then, you know, you don't have H1, so the restriction is already globally generated, so you win. Of course, the interesting case is that V dot F is 0, and pi of V minus F is actually less than 0, and chi of V is at least R plus 2. Again, that's the interesting case. When you have R plus 2 sections, then you are globally generated. And there's one more exception. If E is equal to 1, there's one more exception, which I don't quite care what it is. So again, the main meat of the thing is there, just like some exceptions that you need to think about. So you see, the reason why we were interested in this question is like the problem here that I don't know how to solve is classify ample vector bundles. So you see, I don't know this even on P2. You know, we know what the ample line bundles are. They're often OF1, OF2, OF3, and so on and so forth, yeah? But we have no idea what the ample vector bundles are. But you see, so the hope was that by classifying globally generated vector bundles, you could come close to it. But the thing that you have to be careful is that there are bundles on P2 that are ample but have no sections.
What do you mean ample then? I mean, does it mean that?
Well, so here's an example, yeah? So you take O of minus E, 2 copies, and then some covalent. Okay? So theorem of Giesecker is that if V is sufficiently large, then V is ample. Okay? And this has no sections. Okay? And then, even in this basic case, I don't know how large D has to be. I know that D has to be at least 7, but I don't know whether 7 is enough. So, here's a problem for you to solve by next time. How large does D have to be? Large does D have to be for V to be ample? Okay? But in any case, you see, of course, once you take enough symmetric products so that they become globally generated, then of course they have to lie in one of these moduli spaces. But I don't know. I don't know how to classify the ample vector bundles, and it's an interesting problem that I think people should think about. And maybe let me stop there. Next time I can say the applications to Ulrich bundles and things like this. So.
I noticed that you have only 3 factors there also. Right?
What, 3? No, it's 4. 1, 2, 3, 4. It has to be the same as the length of a strong exceptional collection. Yeah?
Right, exactly.
Yeah?
That's what I wanted to say.
Yes.
That's the length of this.
That's right. Here you have the standard exceptional collection O of 1, O of 2, and this is saying that you can give a resolution of this thing in terms of these. And here you have the strong exceptional collection O of minus F. I'm writing it backwards. Let's write it like this. O of minus E plus 1F, O of minus EF, O of minus F, and O. And the statement is that you can do it in terms of this exceptional collection. You see, in this case, there are many exceptional collections. It's not just enough, this is special. Just like O of 1, O of 2 is special a little bit.
As long as we, well, no. Are there any other questions? All right.